Okay, good morning, everybody. So today, Stuart and I are going to be talking about probably our least favorite subject, which is Java serialization. So this talk is entitled, What We Hate About Serialization and What We Might Do About It. The program left out the word might, so I don't want to overpromise that there's a plan here, but this is a problem we've been thinking about for many years and are starting to get a handle on how we might approach it. So this is how you know we work at Oracle. So you've seen, various folks stand in this room and talk about how much they hate Java serialization. In the past, you've seen myself or Mark or Stuart or Bloch get up here and say serialization is terrible. And in the Ask the Architect panel, which will be this afternoon, invariably somebody asks, "What's your least favorite feature about Java?" And we don't even have to think about it. There's, the answer just immediately comes out. And it's almost sort of a rite of passage as a sort of luminary speaker in the Java community to say something nasty and clever about serialization. And it's kind of a way of processing the trauma, I think. So we all hate serialization. Everybody hates serialization, right? Even Gollum hates serialization. So we're going to talk a little bit about why exactly we hate it, but why we can't necessarily just kill it, and how we might do it better. So it's important to distinguish the concept of serialization, taking an object graph and turning it into a byte stream, from the mechanics of how Java serialization actually works. The concept of serialization makes total sense. You have an object graph in memory, and you want to persist it. You want it to save it to disk. You want to send it across the network. You want to store it in a database. And that's a totally reasonable thing to want to do. And in fact, if Java didn't have serialization, it's quite possible I wouldn't be standing in this room today. I think serialization was an essential part of Java's success. It's what made RMI and EJB remoting possible. But, there's an old saying, today's problems come from yesterday's solutions, and so this talk is mostly going to be about today's problems. The problem with serialization is not the concept, but the approach. The way it was done was pretty much a disaster. It led to a number of serious problems, most of which have to do with undermining the integrity of the object model. So it undermines encapsulation, which is an important way that we manage complexity in our code, in non-obvious ways. It makes it harder to evolve classes that are serializable. It's almost impossible to reason about security in serializable classes. Even experts make mistakes when reasoning about serialization security. As a language designer, I hate it because it interacts with every other feature we add to the language. I would say probably a good almost 20% of the effort we spent in the Lambda project had something to do with the interaction with serialization, which was just a complete waste of time. But the really awful thing about serialization is this last point, which is it interferes with our ability to read the code and know what it means. And I'll pause to let that sink in for a minute, right? We want to be able to, it's not an unreasonable thing to want to be able to read the code and have confidence you know what it does. And with serialization, you really can't do that. So I'll talk for one slide about the good stuff, and then the whole rest of the talk will be about the bad stuff. So if serialization is so terrible, why did we do it in the first place? And in order to really understand it, you have to put yourself back in the mindset of programming in the 80s. So how many people here were programming in the 80s? Okay, old man war story coming. Okay, so, back in the 80s, persistence was a really hard problem, and every application had to do it. So if you had an application that had an in-memory document, it was reasonable for your users to want to save the document and to load the document back in. And in order to do that, you had to write a lot of really fiddly, complex, error-prone code to take the in-memory representation and spool it out into some proprietary custom binary format. And if you get it wrong, you're basically out of business, because if your application gets known as not being able to save stuff, that's pretty bad. I knew this guy back in the 80s, and this guy worked for Lotus. Lotus was the predecessor to Excel, sort of the killer app for PCs. His full-time job was file save. That's all he did, was maintain the file save code. And what an awful job, right? error-prone, it's fiddly, it's not particularly glamorous, and again, if you get it wrong, it's a disaster. And I'm sure his manager didn't like paying his salary to do this, to do this thing either. But it was a tremendous amount of work to maintain, persistence code, and it was always ad hoc, right? And what one of the many things that objects promised us that they were going to solve was, we're going to make this persistence problem go away. That if you have a system with introspection, as the Java object model does, instead of each application writing its own ad hoc, error-prone serialization code, persistence code, the system could just look at your object and say, oh, I know how to persist that, and do it recursively. And it actually did work mostly, and this was an enormous benefit. That reams and reams of horrible code you didn't have to write and didn't have to test, but it came at a cost, right? And the costs, in some sense, this whole talk is about the costs. So I try to condense it down to one slide. The main problem with serialization is it is extra linguistic. It is outside the object model. State gets extracted by reflectively scraping fields, and objects get reconstructed by magic, where it magically creates an empty object without calling the constructor and magically rewrites the fields. And it magically bypasses the accessibility model, even if your fields are private, even if they're final. And, serialization is this, big tangled ball of stuff. It encompasses graph walking and state extraction and wire encoding, and it's all or nothing. You can't say, I want all serialization, but I'd like to use JSON for my wire encoding. You've got to take it all, right? And the encoding it's tied to is not a particularly pleasant one either. And then on top of that, it's hard for programmers to use. And if you're doing anything but the most basic form of serialization, you have to write methods like read object and write object, and they're hard to do, they're hard to get right, and it's just too easy to get it wrong. So, great idea, but the execution had a lot of costs. And I'm going to hand it over to Stuart, and he's going to talk about some horror stories that hopefully will, turn your hair white. And then we'll talk a little bit more about what we might do about it in the future. Take it away, Stuart.
Okay, thanks, Brian. All right, so let me start off by running through a quick overview of the mechanics of serialization. Conceptually, it's actually kind of simple. Of course, the devil is in the details. But basically, let's say you want to serialize an object. Here's what happens. So you start off with this first object, and the serialization framework reflectively looks at all the fields and grabs the data out. So we say scraping the data out because it doesn't use any getters or anything like that, including the private fields. So it grabs the data from the private fields. If any of those fields refer to other objects, then it recursively serializes those objects. And along the way, if you're walking this graph of objects, if the serialization framework runs into an object it has seen before, well, it keeps track of objects it's seen. If it runs into an object it's seen before, it says, oh, I've seen this before, I'm going to write a back reference into the serialization stream. Okay, what happens when you deserialize? All right, kind of the reverse, but it's interesting because the object is created not using a constructor, but through some special purpose ad hoc mechanism where it creates an empty object. And then the serialization data is read and stuffed into the fields reflectively, including private fields, including final fields, which is very strange. Okay, and then it basically does the inverse of what was done with serialization. It recursively walks through the object graph and builds things up. And if it encounters one of those back references, it says, oh, I've seen that object before. It plugs in the reference to that previous object, and on it goes. All right. So I want to call your attention to a few things, if I haven't done enough already. This idea of reflectively scraping data out and stuffing in is something that does not exist in the programming language. This idea of creating an empty object with all default values for its fields, not using a constructor, is also something that does not exist in the programming language. What could possibly go wrong? Let me tell you. All right, what I have here is a thread-safe class. We have a final field that is initialized. It is initialized at object construction time, and all access to that field is done through synchronized methods. So that object, the tree map, should be confined to this object, and it's all protected by synchronization. So this object should be thread safe, right? No, it's not. When you serialize this object, kind of the serialization framework effectively adds some code that says, oh, I'm going to go in and scrape data out of your fields, and it doesn't do any synchronization. Well, how does it know, right? It just grabs it reflectively and starts walking through there. So now what you have is unsynchronized access to shared data. Your class is no longer thread safe. Okay, one of the things that we learned very early on in Java programming is establishing invariants in the constructor. So we have a simple range class here. It has a start and an end. And we want to enforce the invariant that the start is always less than or equal to the end. So if start is greater than end, we throw an exception. And then we assign the fields. So the preconditions are checked in the constructor. The fields are final. Therefore, this class will always be valid. Correct? No. If you deserialize this object, the serialization framework simply reads the data out of the serialized stream and stuffs it directly into the fields, and no invariant checking is done because the constructor is never called. Therefore, you can create an invalid range object using serialization. Okay, this is a little bit more subtle, but if you have it's a very simple example, a class that holds a date object. It has a final field, and the date field is initialized by calling new date. So this refers to Java util date. Let's not talk about the issues with that in particular. But this code says, I'm going to create an instance of java.util.date and put it into a final field. Therefore, this class will always have a reference to an instance of a java.util.date, right? Wrong. So when the serialization framework deserializes something, if it sees an object in the data stream, it will instantiate it, and then it will reflectively assign references to those fields. And if the object it is assigning is a subtype, it will happily assign it to that field. So malicious code could modify the serialized stream and create a subclass of date, and that subclass might have different behavior, and it could stuff a reference to that subclass of date into this field, thereby changing the behavior of the deserialized object and making the class do something unexpected. So in this case, we return a random time instead of some time value. So, okay, we've broken the invariance of this class in yet another way. Okay, so here's a variation of that class. Let's forget about subclassing. Let's assume that the date class or whatever you're using is final, and we prevent subclasses from being created somehow. So again, we have a final field, and we initialize it in the constructor. And by creating a brand new object and storing that into the field, and do some invariant checking afterwards. But the key point here is that we are creating a brand new object, and so we have the sole reference to it. And then we put that into the field. Therefore, this object has exclusive access to the date object in that final field. There's only one reference in the entire system, and this object owns it. Therefore, that date can never be modified out from under us. Right? Wrong. Remember what I was saying about backrefs before? Well, a malicious stream could add back references to objects that have already been created. So we can just drop in a couple extra backrefs into the serialized stream and steal a reference to this object that is supposed to be internal to this class. And now that somebody else has a reference to it, it can go modify it. So we've broken this class yet again. Okay, so what do we deal with, or how do we deal with this? So earlier Brian was talking about writing a read object method. This is a special aspect of the serialization API. You have to add a special weird method that is private, but it is called reflectively by the serialization framework. And so what this does is it allows the class author to write some additional code to to do some additional checking. And so if you look at this code, it does a little bit of magic, reading stuff off of the input stream. Default read object populates the fields. And then we kind of do the same thing that we did in the constructor. We create a defensive copy of the date instance and then store it into the field. But since we are storing into this field using an ordinary method instead of a constructor, we can now no longer make that field final, which is kind of irritating. So we have to remove final from that field. And then we also have to make sure we do the invariant checking again. And if for some reason this date is invalid, we throw a different exception type, invalid object exception. But see, the point is here, though, we had to write a bunch of extra code in order to make sure our class defends against the things that I talked about on the previous slides. So in his book, Effective Java, Josh Bloch spends quite a bit of time on this. There's an item number 88, which is write read object methods defensively. And so you saw an example of that on the previous page. And so it covers these issues in pretty good detail, and it makes some good recommendations. In particular, if you have a serialized object, you probably always want to write a read object method. Do things like make defensive copies of the input data, and that defends against things like the backgraph attacks. And then once you've made the copies, do the invariant checking over those copies. So that is helpful, but again, you've had to write a bunch of extra code, and it's easy to forget to do that, and it's slightly different from the constructor, so you have to kind of look at the constructor and the read object method and make sure they're doing the right things, even though they can't be the same thing, and that the fact that they're different leads to errors. So anyway, the thing about item 88 is it's all great material, so this is not a criticism of that book and the information in Effective Java at all. Good material, good suggestions, good rules, and good recommendations. But they're not enough, because even if you add that read object method that I showed you and throw an exception, if you violate an invariant, an attacker can still get his hands on an invalid object using finalization. So this is a wonderful thing. Finalization, if you're not familiar with, is if an object is about to be garbage collected, then the system can call the finalizer method on it. And one of the things about that mechanism is that it is possible to resurrect an otherwise unreachable object. So imagine you're deserializing something, your read object method gets called, the object has already been created. Its fields have values. It is a valid object, but you've decided, okay, this object is semantically invalid because the date is out of range or something like that. So you say, okay, this is invalid, I'm going to throw an exception. And what that does is it deprives the caller of whoever wanted to deserialize this object and use it. That caller no longer gets a reference, he gets an exception instead. We still have an object on the heap, but nobody's referencing it anymore. Well, that's okay, because it'll eventually get garbage collected. Unfortunately, what someone can do is add a few objects to the stream and plug those into your object graph. And if one of those objects is finalizable, then that object will keep the entire graph alive. And when the finalizer gets run, it can resurrect the object. And an attacker can get his hands on an object that you wanted to throw away. So note clearly here, this is not because you are using finalization. This is somebody else using finalization to attack your class. So you can defend against this, but you have to write even more code, which I'm not going to bother to describe here, because it just makes things more and more complicated. All right, so what have we gone through so far? We've broken thread safety, we've bypassed constructors, we've injected malicious subclasses, we've defeated object containment, we've made things so that we've always told you, write immutable object, use final fields. If you do this, you can't use final fields anymore. And we've gone through a way of resurrecting invalid objects that you wanted to discard. So this is a pretty good scorecard for why we don't like serialization. So what happened here? So when serialization was developed, it was intended to be simple. And really, the idea of saying, oh, all you have to do is add implement serializable to your class, it's very attractive. But it only gave the appearance of simplicity. And as you can see, there's lots and lots and lots of hidden complexity. And the code that is not there can hurt you. It interacts very badly with other language mechanisms like finalization. And so in order to defend against this, you have to write lots of extra difficult and error-prone code. The bottom line here, as Brian said on an early slide, serialization uses an extra-linguistic mechanism for doing its job, and that undermines the integrity of Java's object model. That's why we hate it. All right, so at this point you might say, okay, yeah, let's just throw the whole thing out and use JSON. Well, that's not really a solution at all, because JSON is merely a wire encoding for this serialized information. And I haven't talked about wire encoding at all. All of those things that I talked about in the preceding several slides are problems about the interaction between serialization and the object model. Wire encoding is completely orthogonal to that. Now, you could use JSON in a particular way if you loaded it into a DOM tree and picked data out and created your own objects. That actually would be safe. The fact is, nobody does this. We want to have a framework that will read JSON or whatever, like XML or YAML or whatever you want. We want to have a framework that reads all that data, marshals it all up, and creates objects for us, because we don't want to have to write that picky, boilerplate, error-prone code. So the problem is, if there's a framework that does that with, say, JSON instead of Java's custom serialization format, then it has exactly the same problems. Because of this convenience, how is that framework going to create those objects? And in fact, there are other frameworks out there that create objects reflectively. And like there's this one framework where it says, oh, you have a no-arg constructor. Even though it's private, I'm going to make it accessible and call it and create an object that way, and then stuff data into those fields reflectively. So there are other frameworks that call set accessible and stuff data into your objects just like the serialization mechanism does in Java. And they have exactly the same problems. What do you know? And so this isn't just us saying this. Some black hat researchers did some research into JSON serialization frameworks. The format used for the serialization is not relevant. It can be any of these other ones. Attackers can get remote code execution opportunities regardless of the data format that's used. So now there's a completely separate discussion about what the wire encoding should be. There might be good reasons to switch. Instead of, there's some problems with Java's custom serialization format. Many people like JSON for a bunch of reasons. But really, that's a completely separate discussion. Again, the point is that the serialization framework and how it relates to the Java object model is where the problem is. And so regardless of whether it's Java serialization, which has the problems I described earlier, or some other framework that uses reflection or unsafe or something like that to create and populate its objects, they have exactly the same problem. So doing something like switching to JSON, it doesn't help. It's going to, if you have a framework that is simple and convenient to use, regardless of what wire format it uses, it's going to give rise to exactly the same issues that arise in Java serialization. Okay, so now I'm going to turn it back over to Brian, and we're going to talk about the programming language.
Yeah, thanks, Stuart. So I hope you're all sufficiently terrified. So I sort of misspoke a little bit at the beginning when I said there was an obvious answer about what was the worst feature of Java, because Stuart brought up the other worst feature of Java, which is finalization, right? And, there's a pretty good argument to be had. But like when you have an exploit that involves a bad interaction with serialization and finalization, that's pretty ugly. So, okay, so what might we do about this? So in order to address the problem, we kind of have to step back from it and look at what were the root causes, and Stuart identified them pretty well, that serialization goes around the object model and makes it and works against the programmer in that way. And so, I'm going to talk a little bit about some thoughts about how we might have done it right, knowing, if we knew then what we knew now. Big disclaimer, this is not a plan, this is an exploration. Hopefully it may turn into a plan in the future. So the key thesis is if we want serialization to be able to be safe and reliable, we have to bring it into the object model. It has to be something that is part of the design of your class. When you sit down to write a class, you're thinking about all of these things. You're thinking about what is my representation? What are my invariants? What API operations am I going to expose to my clients? And one of the things that you should be thinking about when you write that class is, what is my offline form? What is my serial form? What does my external representation look like? In other words, if I'm going to serialize this class out to disk, what data do I want to be part of that offline representation? And how does that relate to the in-memory representation? And I think it's essential that the class author be in control of this, that this is part of the design and the implementation of the class, and it has to be natural, and it has to be something that readers can look at the code and say, I understand what this code is doing. All right, these sound like reasonable high goals. How might we do that? As Stuart said, the root problem is magic is dangerous. Serialization reads object state by magic, reconstructs objects by magic, magically bypasses the accessibility model. It's happy to deserialize private classes and all of that. And the problem is that we as humans don't reason very well about behaviors outside the system. We think we know what a constructor means. The example Stuart showed about invariants, we're all trained to look at that code and say, yes, the state is private, it's confined. This class is the only class that can access it. The constructor checks the invariants, therefore everything's great. This is all how we're taught to program and reason about programs. It needs to work that way, because if it doesn't work that way, we are going to get it wrong. And so what we want to do is take all that implicit code, that serialization sort of foists upon us, and surface that, hopefully not in too verbose a way, into the programming model where we can reason about it and control it. So this needs to be part of your design process. It needs to be part of your code, and it needs to be something readers can see. So what is it that the programming model should capture? Well, I posit that what you should start with is, what's the serial form? What's the external form, the offline representation? One of the sort of bad assumptions that default serialization makes is that, 99% of the time people want their in-memory representation and their offline representation to be the same. And then it gives you an escape hatch mechanism, read object, write object, to do something different. But sometimes they're the same. Yeah, that's true. But sometimes they're not the same. Sometimes it makes more sense for the offline representation to be different. This is a data model in consideration. This has nothing to do with, what wire encoding am I using? Am I using JSON or XML or whatever? This has to do with what is the essential data of my class? How do I want to store it in memory, which may be optimized for memory layout? How do I want to store it externally, which may be optimized for other considerations? And then, if the two representations are different, I need code to map from one to the other and reverse when we deserialize. And the key thing is this should happen through ordinary Java code. And the reason for that is we all have spent time learning about how to write a good constructor, right? We've all read effective Java. We all know that you should make defensive copies of untrusted inputs. We all know that you should check invariants. We all know that you should fail fast. We've all trained ourselves to write good defensive constructors. So if we've already done all that work to capture all the things about how to make a valid object in code, why can't we just use that code, right? We certainly don't want to have to write it twice. We certainly don't want to have to write it twice in two different ways, as the example Stuart showed, where the constructor and the read object were almost the same, but not quite the same, so you couldn't share any code, right? So we want to be able to use the techniques we know how to use, and if we're lucky, we want to be able to even reuse the code that we've already written. Unfortunately, by default, it's kind of funny. We write these defensive constructors to defend against programming errors, but if you use default serialization and you don't provide a read object method, then the deserialization process is completely undefended. So we're defending against our friends, and we're leaving the back door wide open for our enemies to march in. And that's not a deliberate decision we made. We followed the path of least resistance. You say implement serializable, and you think you're done, and the consequence is you've left the back door wide open. You could write a read object method. It's easy to forget to do it. It's easy to remember to do it and get it wrong. Because it's not a constructor, right? It's not using exactly the same mechanism that we use every day. So, number one is deserialization should proceed through constructors, possibly through the same constructor that clients call, possibly through a different one. This does have a consequence, which I alluded to on the previous slide, which is this makes it much more difficult to deserialize cyclic object graphs. It's kind of my opinion that originally serialization overreached and wanted to be able to serialize any object graph, when really what people use serialization for is sending data back and forth. And data is more well-behaved than arbitrary object graphs. It's one thing to send a copy of something to someone in the mail. It's another thing to put the car on the transporter, beam the car down to another planet, and have it land on that planet with the engine still running. Right, that was sort of the ambitious goal of original serialization, but I think that was a bit of an overreach. Putting a copy in the mail is really much closer to what we all want to do with serialization. So I just talked about shouldn't deserialization proceed through constructors, and I saw a lot of heads nodding because it seems like kind of an obvious idea. So, all right, that's half of the problem. What's the other half of the problem? How do we do serialization? How do we extract state from objects? And so I'm going to do a very brief digression into a topic that I will talk about in much greater detail tomorrow afternoon, which is pattern matching. And this is a feature that's coming to Java. Here's an example of what a pattern match looks like, where you say, is some object a range? And if it's a range, extract its properties, low and high for me, and then I'm going to use them. And this is a useful feature on its own, for sure. That's why we're doing it. But it's also useful as a building block for things like serialization. I'll walk you through what's going on here. This weird expression that you've never seen before combines three things that we do all the time. A applicability test, are you a range? A conditional extraction, okay, you're a range, let me cast you to range, let me extract your properties low and high, maybe by calling getters, or something like that, and let me pull them into variables so I can use them. And this is sort of the missing piece, which is the opposite of a constructor, right? What does a constructor do? It takes state components and aggregates them into an object. Pattern matching takes an aggregated object and decomposes it, deconstructs it into its state components. And that's what serialization wants to do, right? It wants to say, I have a range object. Okay, well, what is my offline representation? Well, it's going to be the low and high ends of the range. So I need some way for the class to decompose the object into that form. I can write that to the serialized stream, and then presumably there's a matching constructor that takes those same arguments, and when I deserialize it at the other side, I can pass those to the constructor, and I'm done. So you can think of pattern matching as the dual of object creation. And, the exact way it might be surfaced in the language, not yet determined, but it will look something like the opposite of a constructor. So let's look at some code. So here's our range object. It has private final low and high, and the constructor checks the invariant. If they're no good, throw an exception, and then initialize the fields. So I would like to use that constructor for my clients. I would also like to use that constructor for deserialization because it does the right things. And implicitly, what I've kind of said is I want my serial form to be low and high. I'd like to make that more explicit in the code. We'll see how we get there. So this might be what the declaration of the pattern match operator looks like, which you notice it looks an awful lot like a constructor, but it operates in reverse. Instead of taking the arguments and stuffing them into fields, it takes the fields and stuffs them into the binding variables, which are surfaced back to the client. These two members, the constructor and the deconstructor, they have the same argument list. And so it means that I should be able to deconstruct an object with this pattern encode the serial form somewhere. When I decode the serial form, I should be able to pass that right back to my constructor and get back an object that is suitably equivalent. So, one of the reasons why we haven't figured out how to fix serialization until now is the language was missing a piece, which, we're in the process of adding, and it's going to be a good feature on its own, but it also is an enabling feature for us to build serialization on top of it. Okay, so, from this example, you can sort of see the shape of the solution emerging. We can use deconstruction patterns to take our objects and decompose them into a form, into the serialized form, which is the form that the object should be serialized as. And then we can have a matching constructor for that pattern, whose descriptor is the same as the pattern, or a factory method, either way, to reconstruct the object from the serial form. And that means we get to validate the state using the techniques that we already understand. And maybe we even get to reuse a constructor that we've already written. So we get to replace a couple of parts of the magic of scraping the fields reflectively out of the object, and the magic of creating an empty object and then stuffing the fields back into it, with ordinary user code that we can read and debug and test. So that seems like progress. Few more things that we have to address before we're there. We need somehow to communicate to the system that the constructor and deconstructor pattern I had on the previous slide are actually supposed to be used for serialization. We haven't said that yet. We don't want to use magic there either. That was one of the other mistakes serialization made with magic members, that read object and write object, they're not members of an interface. They're just magically named members. Well, we actually have a pretty good mechanism for communicating design intent from code to frameworks, and that's annotations. So that would be a reasonable use of annotations. Let me give you another example that is slightly different, that shows that the serial form doesn't have to be tied to the representation. So, for example, for a linked list, the representation is a chain of a pointer to a node, and then the node has a pointer to the next node, and you chase that all the way. That is certainly, well, you could serialize it that way, but no one would want to serialize it that way. That's an in-memory representation, but it's not a good offline representation. A better offline representation is an array of elements. And so I could write a deconstruction pattern that produces a list of elements from a list. And in fact, well, the implementation of that is trivial. I just call list.toArray. And I can write a constructor that takes a list of elements and creates a new list and stuffs the elements in. And what I can do is I can mark these with annotations. Who knows what the annotations will actually look like? But I can mark them. Say, hey, this constructor here, this is the one you're supposed to use for deserialization. And again, I have a matching pair of constructor and deconstructor that the framework can look at and say, okay, if I serialize with that pattern, I can deserialize with this other pattern because their argument lists are compatible, and the serial form is just the common argument list, in this case, array of objects. So, I said, let's bring this into the programming model. This is what I mean. When you read this code, you look at it and say, okay, I know it's serializable. I know how I serialize it because I call this pattern, which may or may not be also usable as part of my public API. I know I deserialize using this constructor, which again, may or may not be part of my public API. And I know that they share this serial form, which is, in this case, is array of object. So, this is code you can read and reason about. Okay, so there's a few more things that we have to bake back into the process. What about versioning? As classes evolve, the serial form is going to evolve. This is something we often forget to do with serialization, and then have to bake it back in unpleasant ways. But once you change, once you have a serializable class and you make one serialized instance, you have no idea. I mean, what serialized instances are floating around out there. There may be instances, sitting in a database from 1995 of your class, and they may want to be deserialized someday. So the programming model should not only capture the current version of the code; it should capture all the past serial forms that you want to be able to deserialize. Maybe you don't want to deserialize them all. Maybe some of them were problematic and you don't want to try to reconstruct them, and that's okay. But someone should be able to look at the code and say, oh, okay, there's this serial form, which is the current one, and there's also this other one, which is a slightly older one. But I also have to have code for how I map that old serialized form to the current in-memory representation. That's also easy to do. You can have multiple deserializers. Deserializers are just constructors or factory methods, and they can be overloaded against each other. So no problem. All we need to do is capture that in the annotation that says not only is this a deserializer, but it's a deserializer for version 23. And then you can read the code and say, okay, this code supports, the current representation is this, but it also supports version 20 and version 16 that have this serialized form. And we don't have to guess about what old garbage is floating around, because the code will say, here's what I support and here's how I map it to the current representation. So that seems straightforward. Wave my hands, right? Okay. All right. What else do I have to deal with? Well, another problem that we have with serialization is access control. In default serialization, a private class in a non-exported package is still effectively public because anybody can deserialize it. If we want serialization to be an ordinary unprivileged library, we want it to not be magic, we either need to make these classes and members public, yuck, we don't want to do that, or provide some way of saying, okay, the class is private, it's encapsulated, but we intend to expose a public reflective way to instantiate it. And this actually should be a familiar thing. We did this in the module system, right? There's a notion of modules that are not exported, but that are open. They're not something you can call in ordinary Java code, but you can invoke them reflectively because your dependency injection framework or your mocking framework is going to reflectively invoke them. So we've already established a notion of there's an API that people call from Java code, and then there are also maybe things that you want to call reflectively, and they can have different access controls. And so this, again, needs to be surfaced up in the code so you can read the code and say, all right, this is private from the perspective of clients, but it's public from the perspective of serialization or mocking or other frameworks, and that's okay as long as it's clear what's going on. So this is another bit that has to be worked out. I don't have the details, but it's, there's a reasonable design space here. Okay, so let me sum up what I've said. If we use pattern matching for state extraction, and we use constructors or factories for object reconstruction, and we use some kind of metadata to communicate linkage information of which members are intended for serialization and deserialization and versioning and things like that, which is a reasonable use of annotations because you're capturing design intent, and we have some kind of explicit accessibility mechanism to describe dynamically public versus statically public, the result is we've taken this big, tightly knotted ball of something, and we've teased it apart, right? So serialization previously combined graph walking, field scraping, encoding, decoding, and object reconstruction. And we've said, okay, let's take state extraction and reconstruction, make that the responsibility of the programmer. And then what's left for the serialization framework is something much simpler. It's just wire encoding and decoding and finding the serialization members, on the class to use. And that's a much simpler problem, and that's a problem that may not need any special magic privilege. So not only does that eliminate the possibility of a lot of security errors, it also makes it much easier to say, well, I want to write a serialization framework that serializes to XML or YAML or JSON or whatever, but I want to reuse all of the all of the mechanics of finding state that are built into the system. And so that sort of lets serialization frameworks compete on the basis of encoding and performance without them having to reinvent in an error-prone way all the things that serialization does. So, okay, obviously it's not all good news. What's the bad news? Well, I said the word explicit a bunch of times. And when you hear a language designer say explicit, you're probably thinking, great, more work for me. Right? Because explicit means more code. Hopefully not a lot of code, but yeah, more code. I talked about cyclic object graphs. It is much harder to do cyclic object graphs if you always want to be deserializing through constructors. My claim is, if serialization is really about exchanging data, this is a problem. This is not a problem. If you want to serialize your whole program as a stateful, running thing, send it over somewhere else. Yes, you need to be able to deal with cycles. But I mean, JSON can't even represent cycles, and that hasn't stopped like 99% of the world from using that for serialization. So I think that's a reasonable restriction, but it is a restriction. And it also means that we can't inherit serialization from our supertypes, which is, on the one hand, great, more code for me to write. On the other hand, you don't necessarily want what your superclass does to dictate your serialization strategy. You'd like to be in control of it. So it does mean a little bit more work for programmers, and it doesn't fix all the problems. There are other fun forms of serialization exploits, that this doesn't address. What it does do is put the problem on a solid footing where we can reason about correctness. Because if we can't reason about correctness, we certainly can't reason about security. And it does actually give us a kind of gradual migration path away, which is kind of nice. But definitely more work is needed to address all of the things people hate about serialization. Couldn't even fit all the things we hate in one talk, right? But we tried. And all right, what does this mean for the JDK? We have to teach core serialization about these new explicit members. That's actually not very hard. We can use this in preference to the old mechanisms. We have a lot of serializable classes in the JDK that certainly have serialized instances out there. So we have to have a compatible way to migrate from using old serialization to new serialization. Typically, we try to maintain a +1, -1 serialization compatibility policy, which means Java 13 should be able to deserialize instances that were serialized on both Java 12 and Java 14. This is a serious commitment that we make to compatibility, but there's a way to do it. Over the course of 3 releases, we can provide forward and backward compatibility by migrating from the old mechanism to the new mechanism. And when a release is only 6 months, then 18 months is a tractable thing to think about as a migration period for a given class. When our release cycle was 3 to 4 years, it was too silly to even think about, so we didn't. But there is a path to migrating the JDK classes. It's not easy, it's work, but it's doable. And then other serialization frameworks are free to glom onto this and say, okay, now the programming model supports serialization. We're going to use those in addition to whatever other things that we do, because the programmer said, this is how I want my object to be serialized. So, okay, summing up, and then we'll have a few minutes for questions. If we knew 25 years ago what we know now, and we had the language then that we have now, we might have done this very differently. So we're now sort of at the beginning of a long road where we kind of think we know where we can take this, where we think we can reduce the attack surface of serialization, where we can make it easier for humans to reason about correctness, and to reduce the complexity of writing a serialization framework, and to make it possible to write them in a non-privileged way. So we think those are worthy goals. We'll see how we do. If you're interested in more, I've written sort of a paper about this. I'll leave the URL up since it's our last slide. You can go read that URL for more, and we have a few minutes for questions. Questions.
What questions do you have?
Question over there. Stand up and shout, sir.
So you have your domain, and then just before you communicate with the database, you sort of flatten everything out and use data objects, and you build your own mapping to get there.
Right.
I don't know whether we've done that to sort of avoid serialization, but isn't this actually a way to actually still use your constructors and still use your domain logic, and still access sort of some frameworks that allow you to convert to JSON or to convert to some sort of data type, while not risking reflection and not triggering the constructors at all. And I wonder what are sort of the use cases for serialization, if this is still a very solid pattern that I see in practice.
So let me summarize the question. The question is, I'm comfortable doing a lot of work to write data transfer objects to transfer the data and nothing but the data across layers in my system. And if I do that, then I don't need all this fancy magic. And that's true. And like many design patterns, they are a trade-off of I'm going to code in a more uncomfortable, verbose way in order to make my code simpler and avoid certain risks. And it's a totally reasonable thing, for you to do in your application. But you probably don't want to do that. You do it because you have to, not because you love it. People, not everybody is willing to write every class twice, right? So you've essentially written every class twice, where every class has an in-memory representation, an in-memory implementation, and then a special object for sending it across layers, whether those layers are within the same VM or they happen to be going to the database or across boundaries. And that's fine. I don't think everybody wants to program that way. Certainly, if no one used serialization, we wouldn't have these problems. But people do use serialization because they want to say, here's my object graph, I want to write it out to a file. And we want to make that easier and safer. So yes, the way you're doing it works, but it's a lot of extra work, and not everybody is willing to do that work.
I think it was Peter Norvig who said that design patterns are evidence of something missing from the programming language, and I think that's what's going on here. We're saying this is so common, maybe we need to add some things to the programming language to strengthen it.
Yeah.
So, I don't know, I guess
yeah, that's fair. Morris?
Ah. So your idea of having a car transmitted to another planet and landing with the engine running was a central part of the original design aims of Java. This was, in James Gosling's head, this was really what he wanted to have happen.
Yeah. By
no longer serializing cyclic object graphs, you're giving that up finally. Is that right?
Yeah, so to summarize Morris's question, aren't you compromising your principles?
Yeah, and
are you compromising someone else?
Yeah, well, but if you remember my segment of the talk, how many principles have we already compromised?
Yeah, so you probably didn't all hear the question. So the analogy about transporting the car to another planet while the engine is still running, wasn't that the original point of how objects were going to save us from complexity? And yes, that looked pretty attractive in 1992. It seemed like a really cool idea, and if we could have done that safely, we might have liked it. But the safely part kind of got lost in the transportation process, right? And so there is a big benefit to being able to say, my program is this big stateful model, executable model that I'm going to ship to another VM and execute it over there. That's very cool, but it has a lot of costs. And so yes, we're aiming lower. We're saying, rather than solving 100% of the cases, we're going to solve 99% of the cases, because we can do that in a safer, more predictable way. Whether it's really 99 or only 62, well, I'm sure we will get that feedback from the community. My intuition is it's actually a pretty good trade-off, but I could just be in love with my own design and I could be totally wrong. And if I am, I'm sure you will tell me. I think that's time's up for questions. So thank you very much, everyone.
Thank you.